Hello, my name is Gabriele Boschetto, and in this video I will show you how we combine atomistic and device level modeling to explore non-enzymatic sensors which are based on MoS2 for the detection of cortisol. In this video I will briefly introduce the scope of the project and the working mechanism of our chem-resistive sensor. Then I will discuss the results related to both materials and device modeling with DFT and TCAD. And finally, I will discuss conclusion and outlook. So this work was carried out in the context of an European project called Smart Vista. The aim of this project is to develop a smart multimodal and non-invasive sensor which is able to monitor in real time the patient health status and the possible insurgence of cardiovascular diseases. Now this is important because cardiovascular diseases are currently the leading cause of mortality in the world. In the bottom right, you can see a picture of a sensor, which is itself made of different sensors. Can be strain sensors to measure the respiratory and heart rate, but also temperature, and some sensors to measure the concentration of biomarkers. Now, this video will focus specifically on the sensors used to measure the concentration of biomarkers. Here we focus on cortisol, but why we focus on cortisol? Because actually it is an important biomarker which is associated with stress and with a possible correlation with an increased risk of cardiovascular disease. And now this sensor is non-enzymatic, which means that it does not rely on the presence of proteins or enzymes to detect the analyte. Instead, we use MoS2, which is decorated with platinum nanoclusters of different sizes. Now, non-enzymatic sensors have the advantage of being generally stable, both to pH and temperature, but the main drawback here is the chemical selectivity. We chose MoS2 as a sensing material because it is ideal to fabricate very compact devices which can go beyond the conventional CMOS technology. Now, as you can see on the right, here we have, let's say, a sketch of a device architecture. It is essentially a backgated FET, and the channel is made of decorated MoS2. Now, when the analyte approaches the sensing material, this will actually induce a change in some measurable properties that we can detect. I will go more in details later. Now, finally, our aim here is to, on the one hand, to assess the suitability of this sensing platform, and on the other hand, to propose a device architecture. Finally, what we aim here is to bridge the gap between material properties and device physics. Okay, here let's go a bit more in depth on the working mechanism of our proposed sensor. This is a breakdown in mainly 4 steps. The first step, number 1, is analyte absorption. So first we have the absorption of the analyte on the sensing material, so the platinum nanoparticle, which is itself anchored onto MoS2. Now, this will induce a charge transfer, which in turn will cause a change in the channel conductivity. This, again, will cause a shift in the device characteristics, such as the gate voltage threshold. These 4 steps occur at different scales, so step 1 and 2 are mainly at the material level, and we can model this easily with DFT. Now, to run our simulations, we use QuantumATK, as it is an easy-to-use and very efficient platform. Here we computed geometry optimization, density of states, absorption energy, and so on, and these are all easily computed with QuantumATK. Moreover, this is very important for our work, we could conveniently integrate our results with DFT into TCAD device simulations. Now here we show some of the results of our DFT simulations with QuantumATK. On the right, the figure shows the optimized geometries of cortisol absorbed on top of decorated MoS2 with platinum nanoclusters of different sizes. Here we focus mainly on platinum 9, 13, 16, and 20. Now what is shown here is the electron density difference, which gives us information on charge delocalization when the analyte approaches MoS2. Also, we are showing the net charge transfer. Now, based on our DFT simulations, we found that cortisol acts as an electron donor to the sensing platform, which means that the charge transfer is from cortisol to the MoS2. Then, by varying the size of the nanoclusters, we found that there is indeed a size effect. Now, the bigger the cluster, the larger the charge transfer. And it is actually the charge transfer, the key quantity, that allows us to link DFT with TCAD simulations, as I will show in a moment. Now, as I mentioned before, while step 1 and 2 occur at the materials level, step 3 and 4 occur at the device level. And thus, this can be modeled via device simulation. And to do so, we use the TCAD as device. To build a physical model of our device, we use material parameters computed with DFT. Some of the parameters were, for example, the band gap, the effective masses, relative permittivities, and so on. This allowed us to have like a physical treatment of our device channel. Then we converted charge transfer computed with DFT into equivalent doping, both with and without the absorption of cortisol. And then we run our simulations. Here we focus mainly on 3 factors, which are cluster size, the density, so how many particles are absorbed on top of MoS2, and the cluster occupancy, which is how many particles are actually occupied with cortisol. We predicted the device characteristics, and the plot on the right is an example of this. Here we show the current voltage curve with devices in which the channel was MoS2 with platinum 20. The different curves here represent different cluster densities, and the empty markers refer to the device without cortisol, while full markers refer to the device with cortisol. As you can see, the device response varies with respect to the nanocluster concentration, and at each of these concentrations, we could actually observe a shift in the voltage. Now, clearly, the higher the nanocluster concentration, and the higher the signal, and thus we expect a higher device sensitivity with a larger concentration. Now, these are actually only like a small part of our results, but this is to give you like a general idea of the purpose of this work. If you want to know more, please have a look at our paper. But in any case, to conclude here, we combine DFT and TCAD simulations to model a chem resistive sensor, which is based on decorated MoS2 with platinum nanoclusters. Now, by carrying out multiscale simulations, we obtain important insights into the physics of the device. Now, of course, there are some challenges here. The first of these being the chemical selectivity of the biosensor, which is to be explored, and the complexity of the cortisol molecule. So there are different ways in which cortisol can interact with MoS2 and the nanoparticles. For the future, we would like to explore the variation of the nature of the nanoclusters. So, for example, varying the metaspecies, exploring alloys, for example. But also we'd like to investigate the chemical selectivity by considering other common interference. This was a collaborative project, so please, I'd like to take a moment to acknowledge all the members of the SmartVista consortium and the HPC facilities to run the DFT simulations. And thank you for watching.